And a fourth one, which is more related to the subject today, which is dark matter and dinosaurs. Now, she's going to talk about this today. I don't know how much she will say about the dinosaurs. I hope something. Okay, so anyway, without further ado, let's give a warm welcome to Professor Randall.
So thank you for that very innovative introduction. What I do think it's important to see where things tie together. And although I'm a particle physicist, I think the field of cosmology has really done very nicely in bringing together certainly particle physics and cosmology. But what I want to convey during this talk is a little bit how it's also, I think, going to be very important in the next few years to bring in a lot of astronomy research. I think it's going to be really important in terms of constraining dark matter. So although the talk was originally darkly charged dark matter, I'm going to just try to give you I didn't know who would be in the audience, so I'm just going to try to give a flavor of dark matter research, but really the research that I've been doing, which has primarily focused on looking at, as I'll explain more, looking at alternatives to dark matter than the conventional scenarios, and I'll try to explain the reasons why I think this is really important today. Okay. And this is work with a number of people that will come up during the talk. Okay, so the first thing to realize, first of all, can everyone hear me? Just want to make sure the mic's working. Great. Okay. So I don't think I have to tell this audience that there's a lot of evidence for dark matter. People have, crazy alternative theories, innovative theories, maybe I should say. But there's a lot of different evidence for dark matter, and there's very few theories that really can match all the evidence. And it really does seem like actual matter, dark matter, is the most acceptable in terms of fitting everything that we've seen so far. It doesn't mean we know what it is, but it's also, of course, not so crazy to think that there's dark matter. After all, why should all matter be kind of the matter we have? And I think that's a really important insight, that we should stop being so prejudiced based on what we've seen and really think about what matter can be out there in the universe. It might be that everything is connected to our stuff, but it might be, in other words, it might be interacting through forces other than gravity, so that it's much more strongly interacting with our sector than we thought. But it could be something totally different. And by totally different, I don't mean totally different in nature. It could just be an elementary particle. But even as an elementary particle, we wouldn't know what it is yet. We wouldn't know, what do we mean by that? We don't know its mass. We don't know its interactions. Is it just one kind of particle? After all, the Standard Model certainly has many different types of particles. And as I said, we don't even know for sure whether it's an elementary particle. So that's the kind of question that we'd like to answer. Now, of course, if it isn't more directly connected to the Standard Model, then it's going to be a lot harder to study. So, and by that I mean study observationally, to really learn about it. So what I'm going to talk to you today about are just other ideas and how we can hope to maybe learn something at least, okay? So I'm just going to start with a very brief review just of the WIMPS scenario, just to make it clear that when people talk about searching for dark matter, they're almost always, and I think this is just beginning to change, but they're really almost always talking about searching for WIMPS. Many of you probably have heard about the 3 standard ways of looking for dark matter, but they're always, all of those are really focused on looking for weakly interacting massive particles. That is to say, particles that interact with our sector fairly directly. It's a small coupling, but it's certainly nothing nearly as small as gravitational. Okay, so all the structures are based on dark matter interacting with our matter at some level, but of course it could be something different. But why do we do that? Well, I mean, all we know is really the energy density in dark matter, and that it doesn't interact a lot with the Standard Model. So the questions we have to ask ourselves are, when we're thinking about what dark matter can be, how do we guide those searches? And of course, as with everything, we're going to guide it by theoretical considerations. and we're going to guide it by observational considerations. The observational considerations are in some way very basic, like we're going to seriously look under the lamppost, because if we can't find it, we're not going to look there. So we're looking for things that we can actually see. Doesn't mean it's necessarily what it is, but we certainly are, I think it's up to us to make sure we rule out all the obvious things that we can actually look for. But then there's also theoretical clues, and those are important to think about as well. Okay. So I think, I'm hoping that this audience is all familiar with WIMPS, so I don't have to explain, but I mean, there is a good theoretical motivation for WIMPS. We know there's a weak scale in the standard model of particle physics, about 100 GeV, about the mass of the Higgs. We know that if there's a stable particle with that mass, it would give rise, under just standard thermal considerations, just cosmological evolution, to about the right energy abundance. I just want to make clear, a lot of people focus on supersymmetric scenarios with the neutralino. It's really true for any weak scale model. Any extension of the standard model with a stable weak scale particle basically has a WIMP candidate. So that's kind of promising, because we know, or we at least expect, there should be physics beyond the standard model. So then we ask, how would it interact? Well, if it really is connected to the weak scale, it might be connected to the standard model. And then you want to look for low probability events where there's some interaction with the standard model. So I only have an hour, so I'm not going to spend a long time reviewing, but I think most of you know about direct detection, where you just look for low probability events, and that just puts a constraint on how strong the interaction with the standard model can be very directly. People also talk about looking for dark matter at the LHC. That is truly, again, based on the optimistic assumption that it's a weak scale particle, that you can have some missing energy. But you can also put bounds just from higher dimensional operators as well. Just by turning around the thermal cross-section calculation, you can get bounds on what kind of interactions you have there. But again, we haven't seen anything. The third place people talk about looking for dark matter, really meaning looking for WIMPs, is in so-called indirect searches. So that's the idea, is that rather than directly interact with nuclei, the dark matter can annihilate. If it happens often enough, maybe you can see the annihilation signals. Of course, you only see the annihilation signals, that is to say what it turned into, again, if there is some interaction with the standard model. So people look for annihilation into either hadrons or leptons or some other thing. And the hope is that if there's enough stuff that can't be explained by astronomical sources, then maybe you can find dark matter this way. So we focus on things that are less likely to be seen, antiparticles, gamma ray signals. The fact is that observations have seen quite a lot. Have we found dark matter? I think almost certainly not. What we've learned that a lot of the astronomical models were not necessarily right. So for example, there were way more positrons that had been predicted originally. The work that I'll tell you about later was motivated by some signal that then went away. But I think by thinking about these signals, it really motivates us to think about what dark matter sources can give. But of course, in all these cases, you really have to make sure what's a signal and what's background. Okay. But I think it has, indirect detection ideas and looking for what we see beyond what was predicted have really precipitated better understanding of astrophysics and also of a range of dark matter models. And like I said, the work I'll talk about is motivated by one of the so-called signals, and the model, I think, is far more interesting than the signal, and survives even though the signal went away. Okay, so just to summarize where we are today, WIMPs are definitely looking less promising. That's not to say we shouldn't keep looking. I think in the next decade, we will pretty much cover what anybody thinks is reasonable in the WIMP parameter space through these direct detection experiments. Assuming it really is around the weak scale. There's also interesting ideas about going to lower mass particles, which are harder to see because of smaller recoil. But it never was the only possibility for what dark matter is. Sorry, I thought I turned off the sound. Excuse me. It always was something that was only one of many possibilities. And of course, people liked it because it's the most accessible of the possibilities. But that doesn't make it right. So it's really worth thinking about what other possibilities there are, what are other theoretical clues, and also, is there any way to test these ideas? So I'm going to focus on some of the recent work I've done. This is kind of half colloquium, half seminar. Okay. But before I go on, I just want to mention one other large class of models that's really theoretically pretty well motivated. I mean, the original WIMP idea was motivated by the fact that weak scale led to the right energy density. Another important coincidence, I mean, that's sometimes called a miracle. Shut up. Okay. But another coincidence that I think is really worth paying attention to, again, maybe it's telling us something, maybe it isn't, is that although we always talk about how, that there's so much more dark matter than ordinary matter, the fact is they're very comparable. If they weren't comparable, we wouldn't actually be talking about them at the same time. The fact is that, when you look at this, they're both reasonable slices. One's about 5 times the other. And maybe that's indicating that there's some similarity between dark matter and ordinary matter. That similarity could be that just like with matter, antimatter asymmetry, maybe there's a dark matter, anti-dark matter asymmetry. And I think this idea is worth pursuing. Again, an interesting aspect of these kind of models is that in order to explain this coincidence, you really want to have similar chemical potentials for both. With similar chemical potentials, you have some sort of interaction, or else there's no reason for that to be true. And if there's some sort of interaction, maybe there's a hope of measuring it. But in some work that I did with collaborators, we showed that it could just be higher dimensional operators. It could be some interaction that happened in the very early universe. In fact, that's probably the most natural possibility. And that would be very hard to see. But so again, I'm going to tell you about a number of different research topics. I'm happy to stay and answer questions. I don't have time to describe them all in detail. So I'm just going to try to give you a flavor of some of the different things that I think are really interesting in dark matter research, and some of which I've worked on. So with Matthew Buckley, we looked at the possibility that there could be actually weak scale particles. Before that, everyone only talked about light dark matter. We showed that that was also very reasonable in the context of this asymmetric dark matter. And with Yano Kui and Brian Chouvet, we showed that why it could really be well motivated by higher dimensional operators, either thermal or moduli fields, etc., that they could naturally give you the connection. Okay. More recently, I've focused on a number of different particles. I'm going to get to the charged dark matter stuff next. But before I do that, I do want to mention flooded dark matter because there is one interesting observational consequence that I think is really worth thinking about, which is the possibility that actually Fermi degeneracy might explain why things look somewhat more chord than cuspy. There's, of course, a question when we look at dwarf galaxies, what is the evidence? Is it really convincing? But it does seem that in many cases, when we look at the centers of dwarf galaxies, the density of matter is much less peaked than we had predicted. That has motivated self-interacting dark matter models. It's motivated looking more carefully at baryonic feedback. But this other possibility is just kind of cute. And it would require very light dark matter. So I'm just going to briefly tell you about that before I move on. Okay. So in this case, it sort of naturally came out. So what we did with Jacob Schultz and James Unwin is we asked a very different sort of question. Rather than, again, this is what kind of clues do we look for? Well, this was theoretically motivated in a very different sort of way. So rather than try to explain some coincidence about energy density of dark matter, what we asked was, suppose there was inflation. We just said, what would we really expect to have happen? Suppose you're inflation. And if you don't, I mean, almost all models, when we think about dark matter, assume some sort of priority of the standard model over the dark matter sector, which if you think about it is a little odd, considering there's a lot more dark matter than ordinary matter. So we want to put dark matter and ordinary matter on somewhat more equal footing. So we said, suppose at the end of inflation, stuff just decayed. Some of the stuff went into dark matter, some of it went into ordinary matter. So we're not trying to explain the exact number. We're going to fit the number, but we're not going to explain it. So what do we think about that? So we're not going to assume thermal freeze-out, decay or subsequent production, and no favoritism to the standard model. So could this agree with observation? Suppose you just had inflation decay. And you had the inflaton or whatever decay into dark matter and ordinary matter. Well, the interesting thing about this is that it actually very naturally motivates the idea that the dark matter sector is cooler. Why is that? Well, the energy densities are comparable, but as we know, the baryon to entropy ratio in terms of the numbers is really, really small, which means that somehow there's a lot more entropy hanging around probably in the Standard Model than there is in the dark sector. And in fact, that's what we worked out, okay? So we said the energy densities are comparable. The entropy, though, NB over S, has to be what we know it to be. And so we combined it with lower limits on dark matter mass, and it really hints at a cooler dark matter sector. Okay. It's really a very simple calculation, but basically the idea is just to look at the ratio of entropies and to figure and just relate those entropies to the ratio of dark matter mass and baryonic mass and NB over S. And that tells you what the ratio of the temperatures are. And it's a very simple calculation. I obviously don't have time to go through everything. But if you look, it's kind of interesting. Because what you find out is that if the dark matter mass is really low, then you would find the temperatures are pretty comparable. And you kind of understand that because if you think about the temperature of a photon versus the mass of a proton, it's really small. And basically that's that 10 to the 9th. It just happens to be about 10 to the 9th, which is also NB over S. So you get, if you could have really small dark matter mass, you would have comparable temperatures. For heavier dark matter masses, then the ratio of the temperatures has to be quite small. So you would find that the dark matter temperature is much lower than the Standard Model temperature. And there's actually a lower bound on what the dark matter mass can be. So you're basically in the region where you can have a small dark matter mass and fairly comparable temperatures, or more reasonable, larger dark matter masses and a much smaller temperature. And again, there's no model building here. This is really just fitting, just asking a very simple question. How can you make both the two facts that we know that the energy densities are comparable and NB over S is 10 to the minus 9 work? That's all we did here, okay? So I'll give you the sketch of how a model could do this, but I do want to point out that this idea that it's cooler is not actually crazy. It's a really interesting thought, especially for those of you who are here for the conference. If you think about it, if you're thinking about string theory models or any kind of fundamental model, it very naturally gives rise not just to one dark matter sector, to many dark matter sectors. Any sector that's decoupled from the standard model is going to be some kind of dark matter sector. Then you have an interesting question. When we measure the number of degrees of freedom, it really looks like it just comes from the standard model. So, and that's the number of degrees of freedom at baryogenesis or when the CMB is formed. So we're talking about light degrees of freedom. So if you really take the point of view that the high energy theory gives rise to all these different sectors, you have two choices. You either have to believe for some reason all those other sectors don't have light particles, even though the standard model does. You can't have photons, you can't have massless particles, you can't have anything. So either there's no massless or light particles in any of those other sectors, or maybe you can get away with like 2 photons, or the temperature is lower. So it seems that having, and of course, rather than think of lowering the temperature of all of those, maybe there's something that raises the temperature of the standard model sector. In other words, dumps degrees of freedom or raises the entropy. That would be a very natural way to address this problem that actually we usually don't think about, but we should have. It's really actually a question. Why don't we see all these other light degrees of freedom? So the simplest model, and again, there's probably many ways to implement this, but the simplest model just has some heavy scalar or some heavy fermion that just redshifts non-relativistically. So it's heavy, while the primordial dark matter is just redshifting like matter. So at late times, this particle can decay, thereby dumping a lot of extra degrees of freedom, just raising the temperature, raising the entropy of the standard sector. So it would dilute the entropy of all the dark matter sectors and solve this potential question of why there's not more dark matter entropy, which is a really interesting question. One really interesting thing about this is that it's a rare case in particle physics where the sector with the particle with the smallest coupling is going to be the most important. Usually, of course, the small couplings are the least important because it's interacting the most weakly. But in a cosmological context, something that has a small coupling will decay later, which means that whatever one particle has the smallest coupling would come to dominate the entropy. And so we kind of jokingly call this the principle of maximum baroqueness, that just something with a small coupling could actually come to dominate the entropy of the universe. And again, I don't have time to go through this, but just coincidentally, we weren't intentionally doing this. It's really simple to have just a seesaw neutrino model that completely matches the parameter space. I mean, the parameter space didn't have to work. In fact, it doesn't work if all the couplings are the same. So for those of you familiar with particle physics and lepton models, I'll just explain very briefly. Those of you who don't understand this, we can talk about it later, or you can ignore it. But the idea is that in the neutrino sector, we know that the masses are somewhat comparable. Mixing angles are order 1. So it's very natural to have a Dirac matrix with all the entries being comparable. If all the entries are comparable, this scenario actually wouldn't work because the coupling would be too big. However, you can still get all the angles to be of order 1 if you mix only in the right-hand sector. So here we have a matrix with one small coupling, but it's the same coupling for all 3 generations, and you naturally get this to work in the region that would match this flooded dark matter scenario. So there's one coupling that's from M tau, one coupling corresponding to M electron, and it actually works, and everything naturally works. The interesting thing in this case is that it very naturally gives you a very light dark matter particle of order a few hundred eV. It's really light. And again, the principle of maximum baroqueness applies because the last one to decay and heat the universe actually is the one that's coupled with the Dirac coupling corresponding to the electron Yukawa. The other thing is it allows for we see that it allows for much lighter dark matter than we usually think about. And it's consistent with everything because it's colder. So the constraints on warm dark matter apply differently because it's very cold. One of the really interesting things about having such a light dark matter particle is that if it's a fermion, you actually would have Fermi degeneracy on the scale of dwarf galaxies. So you can get core sizes that are comparable to the sizes of dwarf galaxies. And Dumke and Urbano had originally done this. We kind of updated and improved the analysis. And I'm not going to go through it, but I just want to point out, so the blue curve is the Fermi degenerate pressure, and the orange curve is the classical pressure. So you see in the inner region, the Fermi pressure would dominate for a light dark matter particle. Stuff is denser, the Fermi degeneracy dominates. In the outer region, you would have the classical pressure dominate. So what you end up with is a Fermi degenerate core with some sort of classical thermal envelope. And so if you looked at dwarf galaxies, they would have some signature that represented this. Okay. So that's all I'm going to say about this previous work. The rest of the talk, no, I turned off my phone. I don't know what time it is. And the rest of the talk, I'm going to talk about self-interacting dark matter. Okay? So I'll just briefly pause and ask if there are any questions before I go on to give you a break. Any questions about anything I've said so far? You can ask later, too. That might be better later on. Does anyone have a question about anything I've said so far? Yeah.
The light masses didn't seem to make sense. I mean, normally, with original hot dark matter, you have masses of order electron volts because you know the number density of neutrinos and photons is comparable. So your cold model would have very smaller number density.
Yeah.
So that massive electron volt doesn't seem to give you the right omega. Because it would give you the right omega if the number densities of photons and neutrinos were the same.
No, it's the number density of baryon. So so you want omegas to be about the same, right? You don't want the entropies to be the same. So I'm getting the number density is determined in terms of the so you have the number density variance. So that's why the number density is so small, right? And so if you have a heavier particle, the number density is lower, and if you have, so it's just think about it, if you had like an EV particle, you would naturally have about the right same number, right? Because it just turns out EV over GeV is about 10 to the minus 9. So if you had an EV particle, you would automatically have the right number if you had the same temperature. So any heavier particle, you're going to have a lower temperature. So we can work through it. It's a very simple calculation, but that's like the easiest example to think about. Okay? Okay, we can go for it. I promise you it works. Okay. Right, but do you see what I'm saying? If you had an EV particle compared to a proton mass, you would naturally have the same number density as you do.
Okay. Normally we have roughly the same temperature for the photons and for the neutrinos.
That's right.
If you give neutrinos a mass of order electron volts, then you get a sensible omega. So if you're suppressing neutrino temperature,
but that has to do with thermal. That has to do with thermal freeze out. There's no thermal freeze out here. We're just assuming that it's an independent sector, so it's not leaving some remnant abundance. We're just doing it purely in terms of its own thermal sector. So that's what's different about that. So you're right. If there are interactions, if there are thermal freeze out, if there were decays, all of this would be wrong. I said I'm not assuming any of that. I'm assuming the simplest model with a really purely independent sector, and that's why it works. Okay? So it's the simplest calculation you can do. It's really just in terms of saying that we know the ratio of entropies and we know the ratio of omega. Sorry, we know NB over S and we know the ratio of omegas. And then if you know the ratio of the dark matter mass and the standard model mass, which is a proton, then you can determine the ratio of temperatures, assuming nothing else happens. Of course, this isn't God-given. I mean, it could be something very different. But we were just saying, suppose I got rid of all the fancy, complicated stuff of saying that this is an extension of the standard model. I said, suppose it really is an independent sector. Could this possibly work? I mean, I was actually just curious about it. Because in some ways, if you didn't know that there was the standard model, and someone just said there's going to be a standard model sector and a dark matter sector, that's kind of the more natural thing to think. You just think, okay, the inflaton decays into the dark matter, decays into the standard model. So could this actually agree with what we see? And the answer is yes, but it only agrees if you have this either very low temperature or very light particle, and usually some combination of the two. Does that make sense? Okay, great. Okay, good. Okay. So now I'm going to switch gears, and I'm going to talk about something else that would be somewhat controversial, which is self-interacting dark matter. And so by that, I mean dark matter that isn't interacting other than gravitationally necessarily with the standard model, but it is interacting at a sizable rate with itself, okay? And why would we think about this thing? Well, I'm not one of the people that's saying, okay, we see all these problems in astrophysics, we have to solve them. I think it's too soon to tell. We have to do a better job with n-body simulations, we have to do a better job with baryonic feedback, and we have to do a better job with observations. What I do think, however, is that there's a lot of survey kind of astronomical observations going on today, and they can actually tell us something about the nature of dark matter. So it'd be really a pity to do these observations and just waste them and not use it for this purpose. And I like to think of, just particle physics guidance. I mean, if we didn't know what we were looking for at a machine like the LHC, where you're looking for events that happen 1 out of a billion times, you wouldn't find them. I mean, it really helps to have some targets when you're doing these searches. And in the case of dark matter, if you don't have a model in the first place, you're even in a bigger bind because, as I'll talk about, especially in the context of the dark disk, the existence of the dark matter affects the structure of the standard model stuff. So you can't just at the end of the day say how much room is there for dark matter. You really want to be able to do everything self-consistently in many of these cases. So you really want to put in the interactions right from the beginning, see what structure you have, and then ask the question, can you distinguish a model with these interactions from a model without them? And I think that's going to be really important, and I think there's a lot of information we're going to get. And so it may or may not be true that there are interactions, but we can certainly learn something about it. And given, of course, that, again, we're talking about something that isn't interacting with the standard model at all, aside from gravitationally, it's really important to think, can we learn anything about that? And I think in the case of self-interactions, we can learn something. And let's see how well we can do. And I think, we haven't finished this work. I'd say the community as a whole hasn't finished this work, and I think it's a really important thing to be doing. People should be thinking about this. Okay, so we can talk in general about self-interactions. People have thought about it, particularly hard interactions. But here's something that sounds like it should have been ruled out, kind of crazy. The idea that there's long-range self-interactions, namely, the simplest possibility would be just the exchange of a dark photon. So just like dark matter doesn't see the ordinary photon, maybe dark matter has some electromagnetic interaction that the dark matter doesn't see. And so this you might have thought was ruled out. Actually, we kind of thought it'd be hard to rule it out. You can always have the coupling be very weak, but we thought it would be so weak as to be uninteresting. For various reasons that I can get into, we were led to rethink it, and by we, I mean Pratik Agrawal, Jacob Schultz, and Francis Cyr Racine. So we were all looking at these models of darkly charged dark matter. So we just had a very simple model. So there's two possibilities that you can think about that have very different consequences, and I'll mention the other one later. But so you have a dark matter charge, just some U1. And again, that doesn't mean there can't be other interactions. We're actually going to start thinking about non-abelian interactions as well. But let's just start with what might be the simplest possibility, which is just a U1. And then some dark matter particle, call it X, that's charged under the U1. So you could just have that particle X in X bar. It's charge neutral. That could be your dark matter. It's just charged. Or it could be something heavy and light, analogous to having a proton and an electron, and some sort of asymmetry. And that's another possibility that I'll come to afterwards. And it was thought to be very constrained. In fact, if you looked at the literature, you would have thought the interesting regions of parameter space were basically ruled out. What I want to try to convince you, of course I might not be able to convince you in this short talk, but our paper hopefully will convince you, that you could actually get away with having something as light as, say, the weak scale that has electromagnetic type couplings. It might even be even lighter than that. I think the real constraint has yet to be done. It turns out, when we've gone back and looked at these things more carefully, it's just everything is more subtle than was claimed in the literature. So I suspect that eventually there will be strong constraints in all of this, but I would argue that at this point we really don't know what those constraints are. So I think it's probably the most interesting area to be working on right now, because we have data, we have interesting ideas, and we'd like to know what's going on, and I think it has to be thought through a little bit more clearly. Okay, so I'll try to give you a flavor of why. Okay. I just want to say the second focus, which I'm going to get to afterwards, has to do with the dark disk, which some of you might know about. It's work that I actually did before this, where we said that only a fraction of the dark matter is charged. And of course, if it's only a fraction, then it's far less constrained than if all of the dark matter is charged. So I just want to distinguish these two possibilities. One is partially interacting dark matter, which I'll talk about afterward, in which most of the dark matter that forms the halo, is neutral. And then there's some charged dark matter that could conceivably collapse into a disk. The other possibility is that it's only the heavy X particle that's charged, and that's the one I'm going to consider first. So I'm going to come back to this partially interacting dark matter, which leads to the disk. Okay. So again, darkly charged dark matter, it's about as simple a model as you can write down. You just have an X particle, it's charged under U1, and it has some mass mx, okay? So we want to know, what are the constraints in the mx alpha dark parameter space? That's what we'd like to understand. So where do these constraints come from? Well, how are we going to constrain how much things can interact? Well, there's going to be some sort of constraint from bullet cluster type things. Again, bullet clusters tells you that at some level there's some dark matter that hasn't interacted enough so that it's passed through when clusters of galaxies meet. The gas is in the center, but then some dark matter goes through. Another interesting constraint, which I hadn't been aware of before, and I think it's good work, but I'll tell you what the problem with it is with it, is the idea that dwarf galaxies can survive. If you have self-interactions, dwarf galaxies that are moving through a halo of dark matter, the dark matter in the dwarf galaxy can interact with the dark matter in the halo and cause evaporation. So in principle, that could lead to evaporation of the dwarf galaxies, so they wouldn't survive. So the fact that we see dwarf galaxies in halos should put some constraint. But actually, what was considered to be the most significant constraint in the parameter space was actually the somewhat ellipticity of halos. We know that the halos of galaxies and also galaxy clusters is somewhat spherical, but there seems to be some sort of triaxial structure in it, or some sort of ellipticity. It's not really clear. In the case of galaxy clusters, the constraint is weaker. So the strongest constraints seem to come, if you just read the literature, from the ellipticity of halos. So we went back and looked at that. Again, I don't have time to go into detail, but I just want to, and we talk about it in detail in the paper, again, that I did with Jacob Schultz, Pratik Agrawal, and Francis Saracine. But this is the kind of thing we found. So there was a paper that was written a while ago where they looked at what's allowed via relic abundance, because after all, you have XX bar annihilating via the photons, via the dark photons. So you have some U1 dark annihilations. And then they asked the question, if you have interactions, does it wash out the ellipticity? And so they did it by looking at how velocity gets transferred from one direction, velocity dispersion from one direction to another direction. So that if you started off with very different velocity dispersions, at the end you would have very similar velocity dispersions. So you can think of this as sort of transferring energy from one component to another, whether it's from some outer region or whether just from one component to another. They looked at both hard scattering and soft scattering, because if you have a U1, you can have soft scatterings. Now, soft scatterings, of course, don't transfer a lot of energy, but you can have a lot of them because you have the entire galaxy or galaxy cluster to deal with. So you have multiple soft scatterings. And they came to the constraint that either the dark matter particle has to be really heavy, in which case you're kind of outside the relic abundance region. They just seemed to think it was very constrained. These guys actually redid the analysis. They found, unless they had mixing to some other U1, again, that it just wasn't consistent with relic abundance. They corrected some of the errors, but then it still didn't seem to allow a very big parameter space. So we went and redid both of those. And so basically, as I said, the previous results had to do with just transferring velocity from one component to another, and they wanted to say, how long does it take for a particle to change the kinetic energy by an order 1 factor after a number of soft scatterings? But the answers were wrong for many different reasons. I mean, some of them were so trivial, it's ridiculous. For example, they didn't take into account the fact that plus and minus charges cancel. Another slightly more subtle thing is that in the galaxy that they focused on, the baryons actually dominate over the dark matter in the central region. So you can only measure ellipticity, only use this constraint in a significant way in the outer regions. But again, in the outer regions, you measure ellipticity better, but the densities are lower. So you have fewer interactions. So this is an important fact that's going to come up again, which is just that when you do these ellipticity constraints, I think it's really important to be doing it as a function of radius, which has been not so emphasized, for one thing, because it's very hard to measure. But the fact is, you really need to do that because the density changes as you go into the outer region, but you measure the ellipticity better. So if you really want to use this as a constraint, you're going to really need to do that. And I think it's also going to be important at the end of the day to do that, to distinguish things that come from potential from velocity, which is a point I'm going to get to in a minute. Okay. So one reason this calculation also isn't right is that they just used the signal decay time. But as these velocities become closer together, or as the energies become more comparable, if you like, associated with the different directions, you actually saturate. And so the transfer is less efficient. So if you really want to figure out how long it takes, you have to take this into account. Because the ellipticities we're talking about at the end of the day are usually not that enormous. So the ratios of the axes are really fairly comparable, maybe 3:1. So the saturation effect is really important. And as I said earlier, the constraint depends on where you measure it. So this is ellipticity as a function of radius for NGC 720. So if you really see what the constraint is, you find that you really, at the central region, you can have almost equal axes. I mean, that's the lower red curve. If you actually put in 2 sigma, you actually look at it as a function of radius, you find the constraint is far less strong than people had thought. That's the saturation. But another really important conclusion that we had is it's not even really clear how to use the ellipticity for a single object, because there's many sources of ellipticity. One is that the velocity dispersion can be different in different directions, but others are just that the potential itself, just how things are distributed in the dark matter, could be very asymmetric. And it's not clear how that washes out. So there could be substructure, dark matter streams, there could be asymmetric accretion. So even if when I present the result, I can't even take this into account. Because I think until you can do a better statistical analysis, having many galaxies trying to really take into account both these effects, you can't from a single object actually tell you know what this is telling you. But if we said that we believe this velocity, here's what our result was. So the dotted blue curve was the original constraint. So the original is the dashed yellow curve there, which is more constraining. We change things by 1 or 2 orders of magnitude just by putting in these various effects. And like I said, we don't even know if we trust that. Changed it to the blue curve. The other 2 curves, the purple curve corresponds to the bullet cluster, and the brownish curve corresponds to the evaporation of dwarf galaxies. But neither one of those are obviously weaker constraints, but neither one of those are reliable either. Why not? Well, for the bullet cluster, you don't know what you started with. Right? We know that some dark matter passed through, but unless you know what your initial galaxies were and the baryon to dark matter ratio in those objects, the fact that you see some dark matter pass through doesn't mean that a lot of dark matter didn't disappear or evaporate, or some of it gets stuck in the middle. So this is, again, something I think we're really going to have to do on a statistical basis. It could be a lot more dark matter is lost, but we just don't know about it. The survival of dwarf galaxy, I think, is a really interesting research project at this point. Because what the people did when they looked at the survival of dwarf galaxies is they looked at the interaction of the dark matter particles in the dwarf with the surrounding halo. And they allowed for multiple interactions, multiple soft interactions. But they failed to take into account the fact that the dark matter in the halo interacts with itself. And especially if you have a U1, that's a much more important effect. Because if you have a U1 interaction, the cross-section goes like 1 over velocity to the 4th power. So the slower stuff in the dwarf galaxy compared to the velocity at which this dwarf galaxy is moving through the halo means that there's a much bigger interaction cross-section. Plus it's denser. So this So you really have to take that into account. So for every time you interact with something in the halo, you have multiple interactions in the dwarf galaxy itself, which means that instead of just evaporating, it's just going to transfer energy, probably cool it down a bit, and make it puff out. This maybe could even be a good thing, because again, it would get rid of very dense regions, perhaps even helping solve core cusp. I don't know. But it's actually a very interesting phenomenon to think about. So some of them might evaporate. Maybe that explains missing satellites. I mean, it goes in the right direction. It's very hard to know what the constraint is unless a more detailed analysis is done. Okay. So basically, we concluded that the constraints were too strong. We actually don't know what the constraint is. But clearly, even taking these constraints seriously at face value, something with weak mass and electromagnetic coupling is allowed. That's far from what was thought before. Now, it turns out that this is a really interesting regime, even without, again, this constraint might be even further relaxed or further enhanced once we do a better analysis. But even with these parameters, though, we find it's a very interesting regime. Why? Because there's something called the Knutson number, which we'd never heard of. KN has 2 letters. It's just one number, Knutson number. And what it is the ratio of the mean free path and the interaction. So and the size of the object, okay? So if you have a mean free path that's much bigger than the size of the object, everything works the way it did in standard analyses. And you can evaluate core cusp, etc., based on that kind of thing. However, here's the really strange thing. If you have a very strong cross-section, as defined this way, and again, we're not talking about strong parameters. We have alpha comparable to alpha EM. But inside the cores of dwarf galaxies, you have very low velocity. So the cross-section goes like 1/v to the 4th. So you can have quite strong cross-section and very short mean free path. But if you have very short mean free path, you don't transfer energy very efficiently. If you don't transfer energy very efficiently, it's almost like there is no interaction. And actually someone did a simulation, Shapiro and Ahn, and it looks like there was almost a duality. Like if you had something that was very strongly interacting, it was very comparable to something that was very weakly interacting. So we thought at first that maybe this regime would be ruled out because it hadn't been considered and it was so strongly interacting, it might just destroy the center of galaxies, dwarf galaxies altogether. It turns out that's not true. It turns out it's a much more subtle thing. So again, this is really worth going back and looking at. The kind of thing that might constrain it eventually is looking at different regimes, like comparing dwarf galaxies to clusters of galaxies and in between, because we could be able to test this 1/v to the 4th dependence eventually. So we haven't done that yet. So it's all a really interesting, much more wide open research area than we had thought. Okay. So the conclusion of this part of the talk is that even for all of the dark matter to be charged with a reasonably strong strength and a reasonably mass, not crazy high masses, it's clearly viable. The constraints are considerably weaker than was said. Of course, it's not reliable, and there's really a lot more to do. Okay? So I'm going to switch gears once again, and I'm going to talk about if only a fraction of the dark matter is charged. But again, I'm just going to stop to see if there are any questions on anything I just said. And again, we can ask questions at the end, but if there's anything that would keep you from being too distracted and confused while I go on with the next part, please ask now. Yeah.
So this thing you say about the stronger interaction leading to less transfer of so this looks like standard fluid mechanics. So basically,
it is standard fluid mechanics. Yeah, that's absolutely.
Can you just get turbulence when you have higher interaction?
I'm sorry. Can you get what?
So basically, very low viscosity will mean high Reynolds number, so turbulence. So
what's the word you're saying? Thermalence?
Turbulence.
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 Yeah. So I don't know if that happens, and I don't know if it did happen if we would know about it. I mean, it's just it might eventually be ruled out. It might not be possible. Again, part of the reason I'm giving this colloquium is because I know there's a lot of people interested in some of these things here, and I would really like people to be working on some of these, both observationally and theoretically. I just think for me, it's very exciting because, we're seeing many ideas of particle physics have been worked out, but I think there's just all these new ideas that applying some of these just very basic particle physics ideas to some of these astronomical scenarios, and we're led into, much more messy situations. But again, we have so much data now that with this messy stuff, we can eventually statistically sort it out. Or if there's some really bad effect or something that would be really widely ruled out, like some sort of turbulence that you could actually see, then that would be super interesting. So I think it's a really good point, and I don't know the answer. Okay. Are there questions at this point? Okay. So I'm going to tell you about sort of, in some sense, where I started with this charge stuff, which was before we realized that all of it could be charged. We thought about a much simpler, well, at least much safer idea, which is that dark matter isn't just one particle. That some of the dark matter is non-interacting, but some of the dark matter could be charged or self-interacting. And if it's just a fraction of the dark matter, then of course the constraints are obviously going to be much weaker because there's less stuff. On the other hand, if you have interacting dark matter, it could be really interesting. So again, we're not assuming it's all of the dark matter now. I'm assuming it's only a fraction. And I say like baryons. And why do I say that? Well, it's a non-minimal assumption, right? You say, okay, we don't know what all of the dark matter is. Why should we think about this small fraction of the dark matter? But if you think about it for a moment, you realize by that reasoning, you would never care about baryons either, because after all, they have only 15% of the energy density, 20% of the energy of dark matter, but we care about it a lot. Why do we care about it? Of course, because we're made of it, but why are we made of it? Because it has interactions. So stuff that has interactions other than gravitational, even if it's only a small fraction, can in principle be much more accessible. So that was kind of what we were thinking, is if you have this stuff that's interacting, in particular, it can act very similarly to baryons, and in particular, collapse and form a disk or form other structures. If it does that, it would be much denser. Even though it's a small fraction, it could in principle be much denser than the ordinary dark matter, and therefore it could be subject to constraints by measuring the gravitational potential. Okay. Our original motivation, just for those of you who think about gamma rays, was actually because there was an excess that was seen at the center of the galaxy in photons. We were trying to see how you could see this in photons and not charge stuff. We were playing around trying to find just a particle physics model that could explain that. We realized maybe we were totally on the wrong track, and really just stuff is denser than we had thought, which makes the constraints much easier to satisfy. And in fact, if you look at any indirect signal, it usually requires dark matter to be denser than we commonly assume. So if it could radiate and cool down, just like baryons could, we thought maybe you can have dark matter that's denser, either in a disk or even in point-like structures, which is something I'll mention at the end. Okay? So that's the idea. Is everyone with me? Okay. So could it cool into a disk? Well, you need some mean to dissipate energy. So again, the simplest option is that you have this darkly charged dark matter. Could be other things that get radiated, but we just assume there's a massless photon and it can radiate. So again, there's got to be a photon and charged dark matter. In this case, however, because originally we were trying to explain the signal, but we want the dark matter. Generally speaking, we assume it's heavy in maybe it's 100 GeV. Doesn't have to be, but let's say it is. In that case, you wouldn't radiate quickly enough to form a disk. It's just like in the case of the proton and the electron. If you didn't have an electron, the proton would not radiate quickly enough to form the Milky Way disk or many other disks that we see. It's really the electron that's lighter that radiates quickly enough, and then the electron interacts with the proton, thereby forming a disk. So again, we weren't very creative. We just said, suppose this dark matter sector behaves like the standard model. So there's an X particle, which plays the role of the proton. It's the heavier guy. And there's a C particle for coolant, which plays the role of the electron. And that's the model. So there's an X and a C and a U1. Because the C is so light, it has to be an asymmetric dark matter component of the model. So some of it can be symmetric because you can have XX bars consistent with the thermal relic abundance. Because C is light, it can't be consistent with the thermal relic abundance. So you need X and C to be asymmetric or some other non-thermal source. Okay. So, again, I'm not going to go through details. Those are all in the original paper. I should say this was with Matthew Rees, Gigi Fan, and Andre Katz. We considered this what we call double disk dark matter, or partially interacting dark matter, but double disk in the case that you can form the disk. There's both Bremsstrahlung and Compton cooling. Again, this is all very similar to just the standard model stuff. I just want you to notice that because the way the rates go, it's inversely proportional to the mass of the particle to some power. So unless you have the light particle, it doesn't happen. The Compton scattering against the radiation, it's important early on. Then the Bremsstrahlung takes over. So as long as you have ionized particles, they can cool rather readily. Okay. And then you can work it out and find some parameter space for which it works. Not surprisingly, the parameter space is actually very similar to the parameter space of the standard model. That is to say, alpha dark is comparable to alpha electromagnetic, and the mass of the C particle is comparable to the mass of the electron. Of course, there's some flexibility, there's some room, but we know those are parameters that let you form a disk in the lifetime of the universe, and that would be true if we call it standard model or if we call it dark matter. Okay. One interesting thing that surprised us, though, that could be different, is that the thickness of the disk, according to this simple calculation, that's not to say there's not a lot of interesting work still to be done in terms of simulations and thickening and gravitational interactions, etc., and instabilities. But if you just take this simple calculation seriously, you find that the thickness of the disk is inversely proportional to the mass of the dark matter particle. Now that's really interesting because it says that if the dark matter particle is heavier than the proton, the disk is thicker. So in principle, it could be much denser. So the idea is that stuff radiates, they emits the C particle, and it keeps collapsing. Now why is that true? Well, if everything else being equal, the binding energy is comparable in the standard model sector and the dark sector, because alpha and M is similar. MC is comparable to ME. Alpha dark is comparable to alpha. So the binding energy alpha squared M is comparable. However, if you have comparable binding energy, you have comparable temperature. But if your mass is heavier, your velocity is smaller. If your velocity is smaller, you form a smaller disk. It's not 1 over the square root of M because of the density consideration. So at the end of the day, it goes like 1 over M. So that's what led us to think about the idea that you could conceivably have a dense disk of dark matter. Now I want to say that there's a lot of dynamics we don't fully understand, but I think it leads to the important observational fact that when one thinks about the potential, one tries to understand all the gas components. They can all have different scale heights. The stars can have different scale heights. It's important to allow a dark matter component that both has a different density than the standard sector, but also a different scale, a different height, a different thickness. So that's an independent parameter. A lot of the constraints were done assuming that the dark matter was just acting like gas, but it's really important to have this double constraint on what the thickness is and the density. After all, if the thickness was really big, it would hardly be distinguishable from standard stuff. So I think having these models again emphasizes some of the ways the observational constraints should be done. And I'm going to come back to some of the other considerations that enter when we think about the observational constraints in a moment. Okay, so again, consequences, you have a dark disk, could be denser, and has a lot of implications. I think the most direct way to look for this are things like the Gaia measurement, which I'm going to come back to, which is just measuring velocities and positions of stars as they go, particularly the measurements in and out of the galactic plane in the vertical direction should allow you to put some constraint on the potential. And I'm going to come back to some work that I did with Eric Kramer that shows you what constraints you get from the Hipparcos data and some of the subtleties that enter when you do this analysis. Okay. Just in terms of the traditional methods, I just want to mention this for those of you in the audience who are familiar with this and think about it a lot. Even for traditional methods, if there is this dense disk and there is some interaction with the standard model, again, this is not necessarily true, but it would be very distinguishable in very interesting ways. So for direct detection, one of the really interesting things is that this dark matter has small velocity and it would be co-rotating, which means that both the phase dependence would be different and the recoil energy would be smaller. So we think about small recoil usually for small masses. In this case, we would have small recoil simply because the velocity is so low. For indirect detection, it would be really interesting because rather than just see things from the galactic center, you would see it throughout the disk. So in both cases, if you did see a signal, you'd be able to distinguish if it's coming from this type of dark matter or ordinary dark matter. But again, this isn't the most robust or general way to look for this because it assumes this additional interaction. The most robust ways to look for it are through the gravitational interactions. So really what you want to do, the most direct thing to do would be to, and it's not the only thing, but it's the most obvious one, is to look at the velocities and position of stars on a statistical basis. Flynn and Holberg and Flynn did this a while ago with A and F type stars. There's a bright enough star population near the midplane, and they put some constraint. But we learned that if you don't really have the model in mind, it actually makes a difference. So why can you allow for this dark disk? So when we first did this thing, you look in the literature, a lot of people said this kind of thing was ruled out again. It's not ruled out. It's not even anywhere close to ruled out. So you have to have the errors on the standard components properly accounted for. And reddening could be important. But one really important thing is that it has to be done self-consistently. It's not enough to just look at what you get and then say, okay, I use kinematics to say there's a constraint on the total mass. Then I measure the gas components and I say the rest is dark matter. There's actually another effect, which is that if there is a dense dark matter disk, it will affect the distribution of the other components. So it has to be done self-consistently. In other words, it'll be more pinched. It'll pinch it in a way that reduces the significance of the constraints in many cases. So you have to do this analysis self-consistently. The other thing that turned out to be very important in this analysis is that if you actually look at the population of the A and F type stars, they're actually moving slightly. And that slight motion means the constraint is very different. First of all, the constraint you impose has to be very different, because the question you ask is the distribution you see consistent with the potential? But if it's moving, then you have to ask how it's moving. But it's moving consistent with whatever potential you assume. So the statistical constraint would be very different, because you're asking something like, how much does it resemble the average distribution? How distinct is this over the range of its motion? But it also means that the actual statistics become reduced because things move in and out of the allowed region. So it turns out that the constraint weakens a lot when you take into account this motion, which again will be something really important to be taken into account when we have the Gaia data in this region. Okay. So, and also the gas measurements were all over the place, and Eric did a heroic job of getting this right. Okay. And I just want to give you some sort of flavor. I mean, this is just by eye. But, basically people were saying that something was... So what would we want to say as a target density for the disk? Well, we wanted some reasonably significant fraction, maybe a few % of the dark matter. I will soon actually mention the dinosaurs, so that gave us some sort of target value, but it doesn't have to be that value. But, the total surface density is something like 60, 70 solar masses per parsec squared. So say the dark matter had about 10 solar masses per parsec squared. So you might say, if you look at the A and F type star, that it looks pretty consistent. But if you look at it with this dark disk, it's more pinched, but it's also pretty consistent with the data. And again, Eric went through and did a really careful statistical analysis, and they're both allowed. Eventually, though, maybe even soon, we'll know a lot more. Okay, and so I think it's really important, these new measurements that are happening now, which are going to significantly constrain the properties of our galaxy. And I should mention that I'm really interested also in what the effect will be of these surveys in understanding not just the disks, but also understanding the self-interacting dark matter models, because I think there will be really significant constraints imposed on those as well. Just where all of it is self-interacting or all of it is charged. Okay. One other thing I'm just going to mention is some work I did with Jacob Schultz having to do with the satellites of the Andromeda galaxy. So one way you know about things is just the motion of stars. Another thing that seems very intriguing, it's going to be very interesting to follow it up and see if it just has a standard explanation or requires something new, is the fact that if you look at the Andromeda galaxy, and it seems maybe even true of other galaxies, half the satellites are approximately in a giant plane, but a giant approximately planar region. So they're not distributed isotropically. Out of about 30 of them, about 15 of them are in this plane, and almost all of them are co-rotating, rotating in the same direction, which is really hard to explain in a standard dark matter scenario. And one way people have tried to explain it is through tidal forces. As things are merging, maybe stuff is being drawn out of the planes, out of the galactic planes, and that's what forms these dwarf satellites. But if that's true, you would expect them to be almost all standard model. But if you measure them, it seems there's some evidence, and again, this has to be done better. It looks like they're heavily dark matter dominated. And clearly, if there's no dark matter in the plane, this would not be the case. In fact, it's even more interesting than that, because not only does our model put dark matter in the plane, but it puts dark matter at low velocities, which means that if you pull stuff out, that stuff is more likely to be trapped into the dwarf galaxies. So even though the dark matter is a small fraction of the matter, if you look, and that's what Jacob and I did, at how much gets trapped in the dwarf galaxies, you see that it's a significant fraction of dark matter, and it works very well. So it's going to be really interesting to see whether or not that's true. Okay. I'm just going to mention a couple of more recent work. Again, I'm really just mentioning this because I'm running out of time, even though I don't have a clock. But I just want to mention that if things don't fragment just into a disk, they might fragment into objects that then go to the center. So with Pratik Agrawal, we're asking whether the point sources of the GeV axis might be explained by these kind of point sources. I'll come back to that if there are questions. I'm just going to go over this now for and it just works. I'll explain that we could fragment, you form objects, they go to the center. More recent work, again with Francis Saracine, Pratik Agrawal, and Jacob Schultz, we're looking at combining. Before I said that if you have the charged dark matter, it's just allowed. That was without the C particle. If you have a C particle also, so that you could have a disk and a charged halo, it's much more constrained. The reason it's much more constrained is that C catalyzes coupling of X to the plasma. And then you get constraints both on the CMB, but also just on structure formation. It can actually reduce structure, and that's a fairly significant constraint. So you have to have things basically recombined by Z of about 6 or so to be consistent with Lyman alpha and dwarf galaxies. Okay, so I'm going to skip that. But finally, because of the dinosaur idea, I'm just going to tell you what we were thinking about there. And again, this is, I'd say, much more speculative than anything else. It's a much less rigorous way to test the idea, but it is very, very intriguing. Okay, so I'll just spend a few minutes telling you about this, and then I'll conclude. Okay, so this is work I did with Matthew Rees, and Eric Kramer and Michael Rowan followed this up in a really interesting study. So let me just tell you what the idea is. So the idea is that if there is a dark disk, there would be an extra tidal force every time the solar system went through the galactic plane. So let me just show you the picture. I should put this earlier. So as the solar system goes around the galaxy, it's about every 240 million years. It goes up and down through the galactic plane. When it goes through the galactic plane, there's an extra tidal galactic gravitational force. It could, in principle, dislodge objects from the Oort cloud at the very edge of the solar system. Their objects are weakly bound. So what you can do is predict, you can see what the function of density is as it goes up and down, and ask what the likelihood is that something gets dislodged, and then see, does this match what we see in terms of the crater record. Now the crater record is reasonably sparse, but there is a crater record, so you can do some sort of statistical analysis to see, is there any periodic effect. In fact, what Eric and Michael did is they followed it up and went even farther than the periodic effect, and they actually allowed for spiral arms. They really just looked at the density distribution as the solar system went around the galaxy and asked, what does it look like in detail as a function of time? So that's actually what this plot is. So this just gives you a flavor of what you get. So you can say, what do you predict, including the spiral arms, that's the red curve, and then what have you actually seen in terms of craters? And there's a reasonably good match. I mean, it's not perfect, it's a reasonably good match, but you can ask questions like, how does it compare to without it? So if you say, what is the likelihood that you get this, the comet shower at 66 million years ago, which is when the dinosaurs died, versus without, you see that you really get this enhanced likelihood if you have 9 solar masses per parsec squared. So just to backtrack for a minute, if you ask, so what do you need? You need something that's both periodic and episodic. So you were looking for a crater record that's roughly periodic on a 32 million year time scale. That's roughly what it is. And you also need it to be episodic. That is to say, you need something that gives a little kick, because you want these peaks. You don't just want something smoothly oscillating up and down, okay? So the evidence isn't perfect, but if you put it in the model and take that into account, you do get an enhanced likelihood that's periodic. There's a lot of debate in the literature. That's because they don't have a model. They don't take into account the priors. Taking into account priors, it does seem to be favored. Then the connection to the dinosaurs is that there was one rock that we're pretty sure is connected to the extinction that happened 66 million years ago. So the idea here is that you have roughly 32 million year period. Maybe we last went through about 2 million years ago, something of that order. So maybe that one was not the last one, but a couple of times back, it went through and dislodged this object. So we're fairly sure it's a great story. It's in my book. I could tell you a lot more about it, that there was a meteorite that was coincident with the extinction. The question is whether dark matter could have triggered this extinction. But really, we're not worried about life on Earth so much. We're just asking a very scientific question of, if you look at the crater record, is there evidence that there is this thing that you're going through this disk every 32 million years ago or so? Okay. And it turns out, this was the work I did with Matthew Rees, it turns out it really does favor it. And like I said, this is the more careful analysis they did. And not only do they find that it really is consistent with around 9 solar masses per parsec squared, which is well within what's allowed in terms of our disk, they found that it really is enhanced likelihood that it happened 66 million years ago with this. Okay. So I'm just going to say a few concluding words. So we're looking at unconventional dark matter. Of course, what's conventional and what's not conventional is just what we define it to be. I mean, we really have no idea at this point what dark matter is. So I think we should be just open to all possibilities and whether we can measure them or not. But if you have these new forms of dark matter, they really open up new search strategies and also new theoretical considerations. I think in terms of these interactions, it's just a lot of, this duality type thing. I just think it's really interesting, the kind of physics that's emerging. So we want to really do both detailed analysis of specific galaxies, and for this reason, I actually think in the end of the day, something like Theia is also where it's going to measure even smaller scales is going to be really important in putting constraints on any kind of interactions. But also the statistical analysis of distributions, because as I said, in many cases, if you don't know the starting point, it's hard to know what you're predicting. But with enough stuff, you can figure out what is the transition from your initial state to your final state given these interactions. So we want star surveys. We want to trace the gravitational potential, in particular for the dark disk, but also for other kinds of interactions. So it's just a different way of looking for dark matter, and it might be our only way of looking for dark matter if dark matter is anything other than a WIMP. Of course, there's axions, there's specific models that you can look for, but unless you have very specific targeted models, this is just a much more general way to find out about dark matter. After all, our only evidence of dark matter is through its gravitational effects, so why not study them in a little broader detail? There's a lot more to think about. I've mentioned many of the things. I just think we really want to do more detailed numerical simulations, velocity distributions. There's a lot more stuff to do, and I don't have time to go into all of that. But I think, whether or not we have any signals that survive, and in particular the one that led to our research didn't, there are really new possibilities for dark matter. And, this conclusion really applies mostly to the double disk dark matter model, which is just a minor modification. But assuming that dark matter is charged is not a crazy assumption. We just thought it was ruled out observationally, but it's not. So I think it's really important and interesting to answer some of these questions and to think more broadly about these models. So I hope some of you are interested enough to do so, because I think I really do genuinely believe it's really one of the most interesting research areas today. I think there's this really nice convergence of sort of particle physics ways of thinking, but also large astronomical data sets. And I've tried to convince you that although we've thought about it a little bit, we really need a lot more deep thinking to really figure out what the implications are. So thank you.
Okay, thank you so much, Lisa, for this enlightening talk. And we'll take questions.
So you flashed briefly in the last slides, but I was thinking, because I think the whole idea behind all these models is to think that the dark sector could be more like the standard sector, right? So with more richness and some dark radiation-like particles. So, you know, the radiation, normal radiation, what it does in the very early universe, it creates, you know, some tight couplings and some acoustic oscillations. So it changes the structure history. If you have something in your model, why wouldn't you expect something like that as well, and a very different structure formation?
Yeah, okay, so that's a great question. And in fact, it would. And so originally, that's why we thought, one of the reasons we thought it had to be a small fraction of the dark matter. Because if you just have X and C, you basically, this is work that Francis Saracine did with others, basically, if it's about, don't forget, it's a little bit cooler, so it will recombine a little bit differently. So if it's about 5% of dark matter, you can get away with it. So if it's some small fraction of the dark matter, it just gives you a small enough effect from that acoustic oscillation that you don't see it. But if you had it be all of the dark matter, of course, it's very different. So even in that case, so that was why we thought, okay, you can't have all the dark matter be charged. But of course, if most of the dark matter is symmetric and it's relatively heavy, then there's not a problem. It's only when you have like a proton and electron, or like an X and a C, that you have a problem. So in that scenario, most of it is symmetric XX bar, and then there's still only a small fraction, less than 5%, which is asymmetric and can actually do it. But having said that, if you really have both of those together and you have the charged stuff X and X and C be charged, then there is a strong thermal coupling. So not just from acoustic oscillations, but just from really the coupling and just reducing the power spectrum, you would get constraints. So those constraints are all there, and we're taking those into account. But it is interesting, though, that if you have just the XX bar model, then the cosmological constraints, the standard kind of cosmological constraint, not detailed structure from later on, but the standard ones, just there's nothing there, because you're right. It turns out, I mean, everyone immediately says, like, doesn't the CMB rule it out? But it's just not coupled to the photons. If you have a weak scale particle, it's not coupled to the photons. Without something light around, it's just even the dark photons, you know, in the thermal context at the time that's relevant for structure formation. Obviously, early on, it's coupled, but it decouples fairly early on, and you just don't see it, which was kind of interesting.
Yeah, so last year we had Nir Sharif visiting here, and
Oh, yeah.
he has also this evidence of periodicity in the intensity of cosmic rays, which just has the same period.
I know, it's amazing. Yeah, so, you know, like, I like to focus on the physics I understand. I'm not sure I understand what the physics is, but I know that, so Nir Sharif talks about really controversial stuff about weather stuff. But in this context, there could actually be something going on, because it's not, I mean, we don't know enough about what the cosmic rays, I mean, you know, then you would have to connect the cosmic rays to the climate, because what he saw is a periodicity, for those of you who haven't seen this, it's periodicity in the temperature, which amazingly is also 32 million years. And the evidence actually looks fairly strong. He likes to explain it through cosmic rays, which might be true, but it would be, you'd need something that has to do with the fact that as you oscillate, there could be less structure. And his is, as opposed to ours, which is episodic, his is actually rather continuous, which would be more consistent with being something like cosmic rays, so that you get a reduced density as you go around. So it might actually be connected. I do find it amazing that he also sees this period. And the important thing, I guess I didn't emphasize, is that if you don't have the dark matter, then your period without dark matter, just based on what we've seen, is more like 55 or 60 million years. To get this shorter period, you really need some extra components, so you have an additional restoring force. And if we want the episodic one, it also has to be thin, the way we've said. But not for his thing. It would just need more matter. In the back.
You mentioned you thought also about non-abelian interaction. So does color charge help for the constraints?
Does what? I'm sorry.
Color charge.
Color charge. we haven't really done the work yet. We want to look at it in the context of the later model, where we want to see whether it can work kind of like an XC model, but without a C. So we don't know yet. You know, like I said, we're just starting from the simplest, and then you can move into more complicated. It could help for things like the stability of the disk, if there are additional nuclear interactions, and you can have feedback, and it gets more standard model-like. But that's not what we're going to do right away. But I don't think any of this is the end of the story. And so we just consider the simplest possibility as U1. And it's really interesting then to go on and ask what we can say about slightly more complicated models.
So I would like to be a bit provocative.
All right, you're the provocative one.
Yes.
Okay, there we go.
If I can. So what I don't understand is why should be some kind of matter.
Why should be some kind of matter?
Because, I mean, I think it seems to me that there is just an assumption that there is some kind of matter there. Something is there, but I remember there was a talk by some years ago by Andrew Lead in the Royal Society. He was clearly saying the fact there is a distinction between dark energy and dark matter, so it's just an assumption that we make. From my point of view, could also be something dark that we don't know what it means, that has two different effects on the local scale, which is what we call dark matter, and on the cosmological universe scale, which we call dark energy. But I'm just saying, because you're an expert, I would like to know your opinion about why should be some kind of matter and not some kind of other kind of energy which has the effect that we see.
So there are two things I have to say. I mean, one is that, you know, in terms of modifications of gravity, those are far more radical than assuming dark matter. I mean, basically, as physicists, I think there's no reason you can't think about whatever you want to think about. But I just think that it's always best to start with the most conventional seeming idea, because no one's going to believe any of the other ideas unless the more conventional idea works. I mean, if you could explain this all really simply with the standard laws of physics and standard matter, no one would ask for something new. The simplest possibility beyond that is dark matter. I mean, after all, why should all matter carry the same charges our matter carries? I mean, in fact, for me, the more amazing thing is that our matter constitutes 5% of the energy of the universe. There's no reason that had to be as big as it is. So I just don't think it's very radical at all to assume dark matter. But if you still say, well, we don't know, then you could just go look at the different forms of evidence. I just haven't seen anyone who's written down a consistent theory that explains everything we've seen about dark matter. That's not to say our models of dark matter completely explain everything. I think that there's a lot of baryonic feedback, baryon stuff that we don't understand to get things like the Tully-Fisher relation. But until we've actually ruled out those possibilities, no one's going to believe any theory that's modified gravity. On top of that, none of those theories are either they're not consistent or they don't explain all the data. And so you have to, I mean, when you present to me a consistent theory that explains all the data, I'm perfectly happy to think about it, but none of them have done that so far. It doesn't mean you can't work on it. I mean, we're not done. But I don't see any reason to think it's that rather than dark matter at this point.
Anybody? Okay, so let's thank Professor Randall.
On that matter, you normally say people change the densities by a factor of 100 or so through relations.
Yeah.
You're just boosting it by some other.
It is similar to warm dark matter, but it's a slightly different effect because it really is for degeneracy. So the whole analysis is slightly different. But we did use warm dark matter to translate into how to put, because it's really a constraint on T over M that you get from Lyman alpha. So we just applied that constraint, and we stole what people had done for warm dark matter to put in this constraint.
Self-interacting and the rest.
That's what we're doing now. So we have, actually, I can give you a preliminary, and it's very preliminary, but basically it turns out it's a huge constraint. Okay? So you have to have either an alpha really small, or you have to have recombination happen earlier on. It turns out it's a big constraint. Yeah.